Okay, thank you. Um, and did we see, sorry, did we see this too? No? Did we cover this? Don't remember.
Yes, we did.
Okay, okay. So Huygens and Rubens and Drude model, okay? And I think we didn't cover this, right?
No, we
Yeah,
didn't.
okay. So we saw two models, right? We saw the Huygens and Rubens that works quite well for low frequencies. Then we saw that we can adapt the model for a bit of higher, like a bit higher frequencies with the Drude model. And then after that, there's at least up to what we saw, mathematically there was not a model that can replicate the behavior of reflectivity, right? But you guys can remember that we saw actually three theories, right? And when we were talking about the theories, I forgot, yeah, here. So we have a last a last theory that can adapt to basically the whole behavior across most of the spectrum, and that was the Lorentz theory, right? And so that's what we're gonna do now, and that is related to bound electrons, right? Remember, the other models were related to free electrons, well, free electrons with damping later, and now we have, or we can relate this to the bound electron model. So remember, free electron theory applies quite well in the low frequency range. But at higher frequencies, we saw it has a lot of limits. And actually at higher frequencies, light is absorbed and reflected by metals as well as by non-metals in a very narrow frequency band. So how can we understand that? How can we understand what's happening? Well, we need to go to the bound electron theory. We need to go to what Lorentz proposed. And he said that actually we're not going to consider now free electrons anymore. So we're not going to consider, oh, so because you are an electron in the outermost shells, then you're not really bound to your nucleus, so you're a free electron, right? That's what we were considering in the other models. Lorentz said, actually, no, we're gonna consider the electrons as bound to their nucleus. So if you put an external electric field, the positively charged nucleus and the negatively charged electron will create a dipole. So they basically will be displaced with respect to each other. There will be an electrostatic force that's gonna counter out that displacement, that separation, and therefore we create a dipole, right? So about the electron, we actually can be compared to a mass that is suspended by a spring, right? So we have the spring being the electrostatic force that is sort of holding that positively charged nucleus and that negatively charged electron. Um, sorry. Now, if we put an alternating electric field, so light, if we apply light to that bound electron model, the electron will be or will start to perform vibrations. And to describe those vibrations, we need equations that deal with harmonic oscillators that I don't know if you guys ever covered it in physics. So basically now, in order to describe what's happening, we need harmonic oscillator equations. And that is because, again, remember, what's happening is that when we introduce light being an alternating electric field into this atom that has a positively charged nucleus and a bound electron, it will start to vibrate. And that vibration can be described by harmonic oscillators, right? So, the band of, you start with a big harmonic oscillator equation, and then you can start solving, and you guys can do what we did in the tutorial on last Wednesday, and you will end up with something like this for epsilon 1 and epsilon 2, okay? You will end up with these two equations that describe, under these conditions, at high frequencies, describe the optical behavior, and that being reflection and transmittance of materials at high frequencies. Okay, so you have here the two equations. These two equations are the Lorentz equations. Okay, now you might be wondering, okay, what do the terms mean here? Well, E is the charge of the electron, M is the mass, and A is what we call officially the number of all oscillators, or the number of all dipoles, right? And you might be wondering, wait, what is that? We just assume, such as we did for the free electron theory, that we have one free electron per atom. You assume here the same. You have one oscillator per atom. So Na is basically the number of atoms per unit volume. It's equivalent, right? Because if we have one oscillator per atom, it's just the number of atoms, right? Per unit volume, obviously, right? So that's what Na means. And then, B naught, B, those are just frequencies. And there's also a new term here that is gamma prime. You guys can see gamma prime here. That is the damping parameter. So that's basically the parameter, the constant that accounts for this model, that basically comes into play to say, oh, wait, so this model is actually considering what we saw, this this creation of a dipole between the nucleus and the electron, and that bounding between the nucleus and the electron. That is gamma prime, and it's called the damping parameter. Okay. B naught is the resonance frequency. Okay, so it's just basically the frequency at which the oscillator is. It's the frequency at which the electron can vibrate freely without an external force, just vibrate by itself. B is the frequency at which we are dealing at. So basically, B is the frequency at which the system is at that moment. And that's it. Then you know the other terms. Epsilon naught is the dielectric constant. You guys don't know all of them. Okay. Sorry. Okay. So these are basically the two optical constants, epsilon 1 and epsilon 2, for this model. Okay. And you can see, and this is actually true for most materials, the absorbance, because remember that epsilon 2 is also called the absorbance, right? And you can see that the absorbance is maximum around the resonance frequency, right? Around that frequency, as I said, at which the electron can vibrate freely without an external electric field, without an external force. So at around that frequency, the absorbance, is always gonna be at maximum. Okay, and that is especially true for dielectric materials. Especially for dielectric materials, you will always see that the absorbance is at its maximum around the resonance frequency. Okay, and this is what we call an absorption band. And have that term in mind because it's going to be very important. This, when you see a peak in an absorbance spectrogram, you know that that is called, when there is a peak, that is called an absorption band. And we'll see what an absorption band is soon. Okay? And that's basically it. And yes, especially again for dielectrics, epsilon 1 is usually around the resonance frequency equals 1, because obviously this term that you see here, the second part of epsilon 1, goes to 0, right, around the resonance frequency. That is when B is around B naught, or basically they're around the same value, so obviously this term goes to 0, and therefore epsilon 1 approaches 1 around the resonance frequency, as you can see. Okay? So, with these equations, let's see some special cases. Let's see actually what I was saying. Let's see what happens at high frequencies. You can see, sorry, that epsilon 2, when we're at very high frequencies, far away from the absorption band, so far away from B naught, you can see that on either side it approaches 0, right? And in that region again, epsilon 1 is just assuming a constant value of 1. Okay. You can see that, for example, here, very high frequency, right? Very high frequency. You can see that epsilon 1 is approaching 1 as well. See, it just comes and the behavior becomes asymptotic, but it eventually, or it's approaching 1 in the far frequency range. And you can see here also, far frequency range, the absorbance goes towards 0. And actually, this is why a lot of materials, for example, when you do XRD, the X-rays are not refracted and are not absorbed by many materials. And that's why you have the specific fingerprint for every material when you do XRD characterization. Right? Okay. Now, let's consider another case. What happens when there is a small damping? What does a small damping mean is if you have the radiation-induced energy loss is very small, then you know that this equation will basically transform into this equation. Because, again, gamma prime in that case is very small, right? So this term just goes towards 0. This term goes towards 0, right? And then obviously you will be able to simplify this with the square here, and you'll end up with this equation. So for small damping, you can see that epsilon 1 approaches infinity near the resonance frequency. This is called a dispersion curve, and this is what you see for many dielectrics such as glass, because many dielectrics have a small damping. So that means the energy loss that they have due to the induced radiation it's going to be quite low. And under those conditions, the damping constant is small. Under those conditions, you end up with this equation, and this equation basically behaves like this. And you can see around the resonance frequency, what happens is epsilon 1 approaches infinity. Okay, in the dispersion curve, you can see epsilon 1 going towards infinity. And if you consider actually for small damping, basically n squared is the value that will approach infinity, right? Because remember, epsilon 1 is n squared minus k squared. So you know that if this term is going towards infinity, you know that the big term must be n, right? So n squared is actually the term. And that is the index of refraction actually is quite high for dielectrics. For many dielectrics, like glass, and that is because of this condition, right? If we have small damping or if we have a small energy loss due to the induced radiation. Okay. Another special case, what happens when the absorption is near the resonance frequency. So you guys saw in the graph before that electrons absorb most energy from light around the resonance frequency, right? Remember, that's why we had the maximum there, right? If we have small damping, actually that absorption band becomes an absorption line. So that band that you guys saw there actually becomes just a line. And that is because, again, B equals or approximately equals to V naught. And so epsilon 2 just becomes this equation, right? You can plug B and B naught, and this will be 0, and you'll end up just with this equation. So instead of having that nice band, you actually have now an absorption line. So it's just, the peak becomes a lot narrower, right? And that, as you can see even from the equations, you can see that definitely makes sense. Okay. Even though these equations and these considerations do have a relationship to quantum physics, they're not really quantum physics. And it's now time to switch gears. What do I mean by that is, actually, if we want to calculate and interpret, for example, infrared absorption, so far what we consider is okay. We consider the model of free electrons, and we consider the model of bound electrons, and that's definitely quantum physics. But we saw that, these theories have limitations. We saw that, for example, at high frequencies, the free electron theory just doesn't apply. Then we postulated that, okay, for high frequencies, so like, for example, high frequencies means around the ultraviolet spectrum. We said, okay, now we need to apply the concept of harmonic oscillators, right? The one that we just saw now. But from the classical mechanics model, that is basically what we've done with these equations that try to describe the behavior at a bit of a macro level, it's not really evident why electrons behave freely at low frequencies, and why do they behave as if they were bound at high frequencies. Who can explain that, right? How can we explain, yes, it works, okay, when you're at low frequencies, use free electron theory. When you're at high frequencies, use the bound electron theory. Okay, cool. But how do you explain that? And that's when the basics of quantum physics appear. And that's what we're gonna see now. Okay. So we need wave mechanics. We need more basic fundamental understanding of this. And for that, we need a bit more of quantum physics. Okay. So And we're gonna focus for that on the absorption of light, right? And so we're gonna introduce now some concepts. So all materials, and remember that we were looking at these diagrams of reflection, right? And remember that reflection and absorption are related. So let's try to explain what happens and how different materials absorb light. And based on that, we're gonna understand, or I guess we're gonna fill the gap in this whole picture of what is happening with electrons and why do they behave in different ways at low frequencies or at high frequencies. So let's say you have a material, right, a solid, and you introduce light on that solid. So you're basically putting photons in that solid. Right? When that happens, so photons arrive to the solid, the electrons in that solid, in that material, will be excited to a higher energy level because of that interaction, right? Obviously, for that excitation, we need empty energy levels, right? Because if not, where are they going to jump to, right? So if we have unoccupied higher energy levels, if I have light hitting a solid, the electrons in that solid will go to higher energy levels. So for such a transition to occur, we need that the total momentum of electrons and photons must remain constant. Remember that photons are not the same as phonons, okay? Photons are particles. Remember that we have in atoms, phonons are, in simple terms, vibrations, quantum mechanic concepts to describe what happens in a crystal. Okay, so we need that the momentum of electrons, of the electrons being excited and of the photons coming in and hitting the solid must remain constant. So if we are at optical frequencies, we know that the momentum of a photon, and remember momentum is related to the wave vector. You may remember this from the first class, I believe. The momentum of a photon, and obviously the wave vector, is much smaller than that of the electron. And so that puts a constraint. And that will tell me how these electrons can move. And for that, we actually have we have three different ways in which electrons move when we have this interaction between photons and electrons. That transition at which K remains constant. So basically, this is your M band or your conduction band. And this is your valence band, your M band. And here is your conduction band. If you have a transition, so if electron moves vertically from the from the valence band to the conduction band, so you have a vertical transition. So that means your K, your wave vector, is constant. If you have a transition at which your wave vector remains constant, you have what is called a direct interband transition. As you may imagine, the name is quite intuitive, right? Because it's direct from band to band. It's an interband from the valence to the conduction. It's an interband transition, and it's direct because it's vertical. Your wave vector remains constant. And if you actually see an optical spectra for metals, most metals actually will have this, a direct interband transition. So electrons can jump vertically from the valence to the conduction band at a constant wave vector. If you see here, for example, right, the smallest photon energy is absorbed by those electrons whose energy equals, you can see here, the Fermi energy. Right? So you have these electrons in the Fermi energy, or sorry, at the Fermi energy, and they can come and jump directly to the conduction band. That is the smallest photon energy that can be absorbed by electrons, right, that are able to jump. And similarly, you can say, oh, when is the largest energy? Well, that is actually for those electrons that are at the conduction band and they actually jump. They make like two steps. They jump from the conduction band, sorry, from the valence band to the Fermi energy. So that's one transition, let's say. And then you go from the Fermi energy all the way up to the maximum point of your conduction band. So that is obviously the highest or largest energy that can be absorbed by an interband transition. Okay. So smallest energy and largest energy. Now you might ask, wait, so are these only the two absorptions that can happen? No, actually we can have, these are called interband transitions. As I said, we can have interband transitions between this whole spectrum of energies here. So as long as I am in the first brilliant zone, this I can have a lot of transitions. So let's say, let me use, I can have this, and I can have that, and I can have that. So I am gonna basically have a lot of these interband transitions. Okay, so that's one type of absorption given by a direct interband transition. We can have another type of interband transition. And for that, we don't deal with photons anymore. We now deal with phonons. Okay. So we know that a phonon, in comparison to a phonon can only absorb very small energies, but is able to absorb a large momentum. Compared to that of an electron, it can actually absorb a large momentum. So when a transition is going to occur between one band and to the other, that excess momentum of the phonon can be transferred to the lattice. So it's basically absorbed from the lattice. So it's basically like you are exchanging a phonon with the solid. So it's really similar, the concept of a photon coming in, right? Like the previous one, a photon coming in, impinging the solid, and then electrons jump into higher levels. Here is basically the same. The thing is that a phonon can come and hit the solid. The problem is that a phonon cannot absorb high energies. However, it can absorb a large momentum. So that excess momentum can be transferred to the lattice. So basically, the phonon comes, hit the solid, It generates a very large momentum. That momentum is absorbed by the solid, and then obviously electrons are able to jump. So it is exchange, right, between the solid and the phonon. For that, the wave vector is not constant. When that is happening, the wave vector is not constant. And therefore, instead of having a vertical transition, as you had before, right? We had a transition, let's say, from this being the valence band, you will have something like this, a transition like that, right? Now you don't have that. You have an indirect transition, the one here, right? Where your wave vector is not constant. But you're still exciting an electron from the valence band to the conduction band. It's just that it's not at a constant wave vector. And that is why we call this an indirect interband transition. However, these transitions, usually, especially for metals, are disregarded because, at least for metals, they're a lot weaker compared to direct interband transitions. However, these transitions are very, very important for semiconductors and many dielectrics. So they basically, and that is obvious, right? Because, you know, metals are conductive, so they will have direct interband transitions. But for those materials that don't have a high conductivity, like dielectrics or semiconductors, then you will have the indirect interband transitions, and they are actually quite relevant for their behavior of absorption of light. Is it clear so far? Okay.
Miguel has a question.
Okay, go ahead, Miguel. Does the excess momentum have something to do with heat generation? Yes, you can say that. We'll definitely in I think last module is thermal properties, so we'll see the relationship between phonons and absorption of phonons with thermal conductivity, and how, you know, in how that can relate to heat generation. But yes, there's definitely a relationship. Any other questions? Okay. Let's look at the band diagram for copper. This is the band diagram. I think we saw it in the second module, I believe. Obviously, this is just a reduced section of that whole very complicated band diagram for copper. So what can you see here? You can see two interband transitions, right? You can see that the smallest interband transition is occurring. If you look at the electronic configuration of copper, you will see that copper has a field D state. So that D state, the smallest possible interband transition occurs from that field D state to that unfilled state just above the Fermi energy. So that will be the P state. And then, you know, you jump after that to the conduction band. Okay. As I said, remember, you have this sort of a small step transition, right? You go first from your field state to the Fermi energy, and then once you're at the Fermi energy, you're able to jump to the conduction band. Okay. So this smallest energy, you know, from the field D state to the Fermi energy. That is, you know, the interband transition with the smallest possible energy difference. That energy, that value of energy, so from here to here, is what you call the threshold energy for interband transition. So it's the minimum energy that you need in order for an electron to be excited from your field band, in this case your field D band, to the Fermi energy level. So this value of energy is what we call the threshold energy. In copper, for example, this value is around 2.2 electron volts, and that is why, if you have that, if you put a photon there, so if you put light there, this value of energy, so this band transition, you stimulate it, so you promote it to happen, and this results in the red color, that, well, reddish color that copper has. And that's why, each metal has its own characteristic color. Because obviously this threshold energy value will change, right? For other metals it will be 3, for others it will be 1.5, and so. And obviously if you put a photon there, so if you put light there, you excite that transition, and obviously you will have, or you will have generated the characteristic color of the metal. Now, if you go at higher photon energies, right, then you have this second transition, right? Once you're at the Fermi energy, then you just put a bit more energy, and then that second transition from the Fermi energy to the conduction band will happen, right? And as I said, you can have many transitions over the wide range of the beryllium zone. So as long as you are in the beryllium zone, you can have many more transitions. This is just an example of one of those transitions, or one of those interband transitions, right? And this being the smallest possible energy and the highest possible energy. Question for all of you: can I have a transition like this, guys? Is this possible?
I would say yes, and you also have it there that it's needless to say that many other transitions are possible.
Yes, but it wouldn't be useful, because exciting it from this level to this level makes no sense, right? And actually, because the quantum numbers are different, this will only be possible if you reach the Fermi energy, right? You can jump from this quantum or this sub-level to this other sub-level only if the other sub-level, or only when at the level at which the other sub-level is reaching the Fermi energy or slightly above the Fermi energy. Okay. We've seen two different bands transition. Yeah, two different band transitions. Now let's look at, I would say, the last method of transition. This is another photon-induced absorption, like the first one, right? Remember, in the first one, we had a photon-induced absorption. But it's a bit different, because in this case, we're not going to deal with electrons going to higher energy levels in the next band. In this case, it's actually those electrons, those transitions only happen, yes, to higher energy levels, but within the same band. So from the bottom of the conduction band to the top of the, from the bottom of the valence band to the top of the valence band. So I'm not jumping to the next band. I'm just jumping to a higher energy level, but in the same band. That, as you may imagine, is called an intra-band transition. And actually, in this mechanism, we have a combination of photons and phonons. Obviously, as you may imagine, you can only be excited. If you're an electron, you can only be excited to a higher energy level in that same band as long as you have an empty state or you have empty states. Otherwise, you know that transition is not going to be possible, right? And that's why this type of intraband transitions usually happen only in metals, because we know that metals are the ones that have unfilled electron bands. Because remember, insulators and semiconductors usually have full electron bands, right? So their electron bands are filled, there's no space for electrons. But metals usually have unfilled electron bands, and that's why these intraband transitions may occur. However, if you have a semiconductor that is highly doped, remember you create those holes, right? And therefore you do have space for electrons to move. And that's why you will have intraband transitions in those materials. As I said, intrinsic semiconductors, their bands are completely filled. That's why they don't have a classical infrared absorption, and that's why insulators have or are transparent in the visible spectrum, right? That's why glass is transparent, and many insulators actually are transparent in the visible spectrum, right? So you can see there, for example, the band for a semiconductor, right? And the largest photon energy that can be absorbed, so Emax, just follow the line of Emax, just follow the dotted line. That is the largest energy that can be absorbed by an intraband transition. So you can see, for example, here, let me show you what's happening is basically I'm here, right? I'm at this band, I'm just jumping here. I'm from here, I'm jumping there. From here, I'm jumping there, right? So I'm just jumping to the level, actually, probably this should be better done like, if I'm here, right, I jump to the same energy level, let's say to here, to the same level of energy than Emax, right? So I'm jumping actually from here to here, right? Yeah, let's say. Or you could also say, right, if you are, let's say you're an electron and you are here, right? You can jump up to Emax. That's the maximum energy, right? So let's say you can jump up to here, right? But obviously you must follow the band, right? So let's say you're jumping up to that point. So your path is basically this, from here all the way up to here, right? And you've jumped from the bottom of the conduction of the valence band to around the top of the valence band. Okay, so Emax is the maximum energy that can be absorbed by an intraband transition. If you have an energy smaller than Emax, let's say if you're an electron that has a smaller energy than Emax, then all of those will be absorbed continuously. Okay. So let's make a summary. At low photon energies, intraband transitions will happen, right? So this case, as long as I have empty or not empty, unfilled energy levels, right? And that usually happens in metals only. Once I reach a critical light energy, and remember that is why we call the threshold energy, we can have interband transitions, right? That will obviously depend on the energy difference of the bands. Remember that interband transitions occur in metals, mainly, especially direct interband transitions. And if we're talking about indirect, then we can have them in dielectrics or insulators and semiconductors as well. Okay. Questions? Is it clear? Okay. We'll do the coffee break at the end of the class.
If the energy absorption in the same band is continuous, in some moment, in any moment, the excess of energy can be able the electrons jump to the conduction band, or no, in this mechanism.
No. If we're talking about an intraband transition, there will never be a jump from one band to the other. No, it must be an intraband transition, and that's why this happens at low photon energies, right? That's why, just the summary I said, intraband transitions happen at low photon energies. These are the only one possibles because we have literally very low photon energy, right? Once we go higher to higher energy of photons, then yes, you can have the interband transition, and then you can have a jump from one band to the other. Now, how do you get the energies for interband transitions, for example, this threshold energy that we were talking about? And actually, you could also get, you can get this with optical spectra, and you can also get with optical spectra the band gaps, obviously. The problem is that it sounds simple, but it's not so simple. For isolated atom in ions, so simple atoms and ions, the absorption and emission spectra are very, very, very sharp. We can easily determine the absorption, the emission energies for atoms. Very accurate, perfect, because we only have isolated atoms and ions. That also happens for molecular spectra. So if we're dealing just with one molecule, very easy to get the absorption and emission energies, and obviously the band gaps. But if we're actually dealing with solids, it's not so simple. Just because, solids are very dense, there are a lot of interatomic interactions happening that splits the atomic level into quasi-continuum bands. It becomes so complicated. And so the spectra that you can get is not sharp. It's not really useful because you just get a lot of data, and the bands are not separated. They as it says here, they're usually like quasi-continuous. You can't really separate the absorption bands. You can distinguish them. So it just becomes a whole mess, and that again is because in a solid you have a lot of particle interactions. You have a lot of density. It's very dense in terms of particles, right? It's not as simple as having one molecule or isolated atoms in ions, right? So sorry, also a plane, if you just get a simple reflection spectra of a solid, you can't really deduct from there the transition energies. Because if you remember, reflection is a function, if you remember the equations that we saw in the tutorial last class, reflection is a very complicated equation that is related to epsilon 1 and epsilon 2, right? If you remember that. And that's why when we're dealing with ions, molecules, and atoms, yes, you do a simple reflection spectra and nice. But if you're dealing with solids, you don't do reflection spectra. You just do the epsilon 2 spectra. That is absorption spectra. Okay. With absorption spectra, you can easily see when basically you can easily calculate the interband transitions or the energy for transitions. You can even see the band gap. So it's a lot easier because obviously it's more clean, the spectrum, right? And actually that stems from the fact that you have these continuities in the energy profile of the density of states, right? And so that is why you have a characteristic spectra for each material, because obviously each material has its own energy profile for the density of states. Okay. So remember, this is just, I guess, a side note on how can you measure this, and it's usually by taking advantage of an absorption spectrum. Okay. Now, how do you measure optical properties? If you start thinking on measuring optical properties, it's actually quite complicated, because let's say solids and especially metals, we know that they are very opaque, right? So you need to take measurements in reflection, right? Not in absorption. You know that light penetrates just the top surface of the metal, usually around 10 nanometers of the metal. So what you're measuring is actually measuring the optical properties at the very surface. And you know that surfaces are usually susceptible to oxidation, to deformation. If you're polishing the sample, you can have any sort of contamination of a layer that was absorbed, and it's complicated. So that's why usually to measure optical properties, you usually need to go to ultra high vacuum, or you need to do a vapor deposition. But you know that also can affect, right? Let's say if you did a vapor deposition, or if you did sputtering, you might be measuring the optical properties of that layer of sputtering and not really of your material. So it's quite complicated to measure optical properties, especially again in bulk solids like metals. Now, let's say, okay, you're a great sample preparator, so you've prepared a nice sample, and you know that what you're gonna get is clean and nice and useful data. But now you have another problem. The most important relevant properties, so the index of refraction, the damping constant K, epsilon 1 and epsilon 2, and all those energies for interband transitions, you cannot measure them by reflectivity. And we said that, in metals, because the absorption is just only on the top surface, you need to measure everything on reflection, right? And it's not so simple to measure reflectivity in a metal, because it's not simple to say, oh, the ratio between reflected and incident intensity. And that's why a lot of techniques have been developed. I don't want to talk about the main three techniques, because I guess that's even more theory on how do they work and how do they operate. But let's say that, you know, with technology, there is being an adaptation to sort of measure reflectivity. You know, obviously now everything is automatic, and there are, I would say, two techniques actually that are mostly well used in academia and in industry to measure reflectivity, right, in metals. And with that, you can actually get something like this, right? Like this reflection spectrum. And let's actually see how these spectra look for pure metals. What happens with pure metals? So you can see for this is for silver, right? You can see that for silver, at small photon energies, so that means energy less than 3 electron volts. So that means around the visible or before the visible range. You can see that the spectral dependence of epsilon 1 and epsilon 2, it's literally the behavior of pure of free electron. And if you remember, this is up to here, up to around 4, right? Around 3.8. If you look at the sort of the last slides that we saw last week, remember that we had the Hagen and Rubens and then the Drude model. And remember that it was literally like that, right? It was just coming from 100% and coming down, up to around 0, right? Percent reflectivity. And then it would just end up there, right? So up to around 3.8, you can see that actually you have that behavior in silver, at least, that behavior of a free electron model. But then beyond that, now you see that it has nothing to do with a free electron. Now you can see what we saw in the last model, the Lorentz model, right? That classical oscillation, harmonic oscillation, that we define as an interband transition. Now you can say, how can you say you have interband transitions, right? Look at the peaks. Remember that when you see peaks, right, especially just look at epsilon 2, right? That's the most important one, because remember, you're measuring absorbance, right? And when you have peaks there, that means you have transitions there. And if we're dealing with silver, you know that those transitions are direct interband transitions, right? So you can see up to there, free electron model, from here onwards, classical oscillator, or I guess being more fundamental, interband transitions are happening. And you can see there the behavior of epsilon 1 and epsilon 2, right? Also, see this, just the typical case for free electrons, and then here this is the whole mess of harmonic oscillations, right? So this you calculated for by the Kramer's chronic analysis, and that is one of the, I said, one of the techniques in which you can measure reflectivity for metals. Okay, now let's look at copper. Look at copper. You can see that copper has an absorption band in the visible spectrum. What am I talking is this band. Look at that peak, epsilon 2 here. Look at that peak. That's in the visible range. Okay? That's why if you remember, that's why we see copper as red, right? We see it so in the visible spectrum. So that and you can see that is around 2.2 electron volts. You can sort of measure from here to here. Actually, just go there, and this will be around 2.2, right? That is the value that we said. Okay, that is the value of the threshold energy for interband transition, right? Then you can see another peak, actually around 4. You can see, let me red. Now you can see this peak around 4, right? That is also another interband transition, but that is the transition from the Fermi energy going up to the conduction band near the L symmetry point, right? L and those are L symmetry point. That's just referring to the quantum states of the atom, but I don't want to get into that. So don't worry about that. But the important part is here understanding how to interpret these diagrams, right? So you can see here reflection. It is not really a marked behavior like you had, let's say, for silver, where it was evident that, let's say, in this region you have a free electron behavior. Here, there's not really a free electron behavior anywhere. You see, everything is really quite complicated. But you can definitely see the peaks, right, of absorption at 2.2 and at 4.4. And then you can see sort of very slight peaks around, what, 10-ish, and another peak around, what, 20 electron volts. But obviously the most relevant are those two, right? Happening at 2.2 and at around 4 electron volts. Look at the spectrum of aluminum. Right? Again, you sort of see here, let's say, two sections that try to resemble the free electron model, right? So you can see in general the behavior, it sort of resembles the free electron model, right? Except in the small energy region, especially here, right? Because here, I guess you can say, oh, this looks like, that looks like free electron model. But in that small region, so that peak that you see here, and you can see it here, around 1.5 electron volts, that is the only part that, let's say, that doesn't behave as a free electron in aluminum, right? The rest, you can say yes, you have a free electron like behavior in aluminum. Okay. Any other questions? Sorry, any questions, guys? Is it clear? So again, the peaks you see here, those are the interband transitions, right? Okay. So now to optical spectra in alloys, right? Because the one we saw before is just pure metals. So let's look at a series of different spectra for a copper zinc alloy. You can see different things here. By the way, the numbers you see there is just the percent of zinc that you have in the material. Okay. You can see 4 peaks there, right? A, B, C, and D. Let's go peak by peak. And let's focus on peak A. pK, by the way, this delta R over R is equivalent to absorbance, right? It's the same as in epsilon 2. So just you guys are clear. So pK obviously becomes the threshold energy for interband transition, right? And if you see, it actually shifts to higher energy with increasing zinc content. You can see, let's say, I don't know, right? Let's say it's around 2.2. Then it shifts to 2.4. Then it goes, well, around 2.42. Then it shifts to 2.5 maybe, and then it's around 2.6. So it is shifting as I increase the content of my alloying element. I am shifting that threshold energy for interband transition. So I will need a bit more energy in order to be able to excite the electrons and in order to be able to generate the interband transition. Okay, so that is, let's say, ET is what we call the energy for interband transition, okay, or the threshold energy. Now, if you just look at the energy, at that energy versus atomic percent of different alloying elements, you can see that there's a linear increase in energy, you know, with increasing atom percent, and that makes sense. You see here that you see here in this behavior, you can see that with increasing zinc content, the energy is shifting towards the right. So I'm needing a bit more energy, and that is something again you are looking at here. That is, let's say, in copper. If we're again dealing with copper, with this copper alloy. You know that transition has to do with the transition from the upper D band to the conduction band, right? So you can see here, interestingly enough, that for example, gallium has 3 valence electrons, right? Versus zinc has 2 valence electrons. You will expect that because you have more electrons, there will be a rise in the Fermi energy, a bit more than, for example, in zinc, if you're comparing it to gallium, because you have more electrons, and that actually happens. So you're raising the Fermi energy. So let's say your Fermi energy was here. Now you're raising it a bit more. So now you need more energy, right? So the higher the valence, at least just comparing between zinc and gallium, and if you go higher to silicon, germanium, you see that they have 4 valence electrons. You actually need more energy. And that actually is, again, because there is a rise in the Fermi level. And that rise is caused by the solid additions, by the alloying element. Right? Just having extra electrons in the copper matrix. And obviously, if I have more valence electrons, if I have 3 instead of 2 or 4 instead of 2, obviously I will need more energy. And so this graph completely makes sense, right? However, there is another interesting fact here, and that is that at least up to 1 atom percent, you don't really have a variation in the energy threshold, so in the energy for interband transitions. So disregarding whatever alloying element I use, I actually have I don't have any variation in my energy for interband transition. And that is because of a screening effect. Because obviously when you have few atomic percent solid additions, that charge that is introduced by the alloying element, it can easily be screened just because you have very few very few atoms. It can be easily screened by the copper matrix. So basically, the copper matrix can say, "Oh, you're here, but because you just have very small percent, it's like you don't matter. I can easily screen you, and it doesn't have any effect, right?" But as I increase the atomic percent, obviously, then there will be an influence. And obviously, I will need higher energy if I want electrons to be able to jump. Okay? So this is what I was talking about when I was saying, oh, a rise in the Fermi energy and that, okay? When you have solid additions, not only to copper, but to other conductors, the d bands will become narrower, right? So there's less interactions between copper atoms. And so you can see actually the d band gets lifted a bit. You see the d band, and now look at the dash line there. Just a small lift from the previous state, right? And you can see now the Fermi energy. Look at the Fermi energy, current Fermi energy level, and look at the new Fermi energy level, right? There is a rise when I add, solid content, when I add an alloying element, I will create this rise in the Fermi energy, and that's why, remember, I increase this ET, right? Before it was only from here to here. Oops. Before it was only, let's say, from here to there. Now I need to go from here to up there. Oops, sorry, to up there. Okay? And that's why you see this increment in the energy threshold as I increase the atomic percent. Any questions, guys? You can see also that when I add alloying elements, the S band lowers, right? But that will be for the second transition, right? So once you are at the Fermi energy, then you have that second transition from here up to there, right? But that is for the second transition. Okay. Now, we saw for A. Now let's look for B and C and D, right? Because you have A. We already saw that for A, so that is the interband transition. Now let's look at B and C. You can see it happens around 4 electron volts. That just, let's say, for this alloy. Obviously for other alloys it will happen on other energies. And now if you look at the transition energy, it actually decreases with increasing solid content. Let's look at the graph. Here you can see it. As I increase solid content, now where is this? As I increase, so as I go down in this diagram, you can see that the peak of B and C is actually shifting. Instead of A was shifting towards the right. Actually, now B and C are shifting toward the left, right? You can see that. So, I have the opposite behavior for this. The transition energy is actually decreasing with increasing solid content. What are these transitions, you might ask? Well, these are these transitions, the one I was talking here. This one. From the Fermi energy to the conduction band. And as you can see, it obviously decreases because why? Because the level of the S band is becoming or is lowering down. And also remember that the Fermi energy is rising up with increasing solid content. So actually this energy becomes quite small. And that's why you see, and actually is a larger effect. You can see it's a very large effect. So let's say curve A, it is shifting towards the right, but it's a very small effect, right? Compared to B and C, they are shifting a lot. Look, when you have 0.5% of zinc, it's at what, around 4. And then you have when you have 18% of zinc, you have that peak at around 3 electron volts. So it's a significant decrease. And that is because, again, you have a rise in the Fermi energy and a decrease in the, in this case, the S band. It can be any other level, but, in the conduction band, just coming down. And that's why you see with increasing solid content, that energy decreases. Okay, is it clear, guys? Any questions? Okay. So let's look at some applications now of the optical properties. To be honest, there are endless applications, but let's look at some of them, right? One of them is, it actually helps me to determine corrosion in certain materials. So I can make use of optical properties to determine corrosion. I guess they are preferred, optical studies are preferred because they are non-destructive, they're simple, and they allow the investigations of oxides, in situ, which is quite nice. And because of if I actually want to measure the corrosion, I don't need vacuum, right? Because that's the purpose. I actually can have corrosion in situ, and I can easily measure the corrosion. So, for example, the graph you see there, it's from an experiment, an electrochemical corrosion of copper in aqueous solution. So you can see the reflectograms there. You can see the evolution of copper oxide, right? CO2O of copper oxide on the substrate, right? And you can see you have a peak around 3.25 electron volts or so, 3.25 electron volts. And you can see that the peak is growing a lot initially, right? If the peak is growing, the absorbance peak, remember, if the absorbance peak is growing, you know that the thickness of that film is growing rapidly at the beginning, and then, it sort of slows down. Up to here, I would say it grows very rapidly, and then, let's say after 16 hours, or I think it's 18 hours, and then I go to 19, 24, 40 hours, the growth rate is slowed down, you don't really think you don't have a significant increase in absorbance, therefore you don't have a significant increase in the thickness of film. So basically, again, this helps me to see how that corrosion is happening, or the rate of evolution of corrosion in, let's say, this case, of copper in an aqueous solution. Okay. So, see, I can make use of optical properties to determine corrosion of a material. Okay. Semiconductors. Right? So you know that intrinsic semiconductors at low temperatures, they have a completely filled valence band, empty conduction band, and that's why they're basically like insulators, right? So there's no intraband transitions, there's no classical infrared absorption, so they're basically insulators, right? And that's why they are actually transparent in the far infrared region. Once I increase the energy of photons, and I eventually reach this, once I eventually reach the gap energy, I start exciting electrons from the top of the valence band to the bottom of the conduction band. A semiconductor becomes opaque, it behaves like a metal, and then you will start seeing absorption peaks due to interband transitions and also intraband transitions. Okay, and so now you can see in the visible and the UV range, you can see the peaks. And then, yeah, obviously this will depend on the semiconductor. You remember that the gap energy can go from as low as 0.2 electron volts to as high as 3.5 electron volts in semiconductors. Okay, so below the gap energy, a semiconductor is transparent. Above, it's opaque. It's like a metal. So let's be specific and let's look at the absorption spectrum of silicon, right? Silicon is an indirect bandgap material. So you can see there you have three absorption peaks, right? Look at the peaks, you have three absorption peaks. They're all direct interband transitions. And remember that actually in silicon, if you go to higher energies, right, you will have both. You will have the indirect behavior, right, where you have different or a varying wave vector, and you will have the direct transition, right? But for direct transitions, you need what? Around 3.4, 3.5. So once you reach there, then you have the direct interband transitions. Below that, so in this range, what you can have is only indirect band transitions. Okay. Okay. Now let's look at extrinsic semiconductors. Remember that extrinsic, they do have donor or receptor states near the conduction or the valence band. So if I go to a sufficiently high temperature, I know that I can have these optical transitions from the valence band to the conduction band, and there will be all these interband transitions happening. So basically, extrinsic semiconductors have more of a behavior like a metal, right? So you will have, the peaks and everything like a metal. That is, I guess, the final note on this. Yeah, I guess this is more on really applications point of view. There are high resistance semiconductors for, let's say, photoresistors or photoconductor devices. So then you use cadmium sulfide especially, or lead sulfide, even though because of its toxicity, it's not really much use, or you can also use indium antimonide. And so you know that if you impinge more light, and again that means if you are giving them more energy, then the material becomes more conductive, and that makes sense because remember you're reaching the threshold energy, right? So you will have more absorbance, and then obviously the material will become more conductive because at the end you're also exciting electrons. So then you can also see the relationship between optical and electrical properties, right? Okay, well, yeah, you might be wondering what's a photoconductor, right? Well, they're using light switches in motion detectors in camera lights, alarms, photocopying, clock radios, basically a lot of electronic devices. Okay. And as I said, optical absorption measurements, so in general, absorption is used for metals widely because it allows to determine, remember, the band gap, also the threshold energy for transitions. And so these absorption techniques and the absorption spectra is quite useful, right, for semiconductors and for metals too. Now, what happens with insulators, right? We know that insulators have completely filled valence bands, empty conduction bands, so there's no really intra-band transitions, right? That is, there is no a classical IR absorption. And we know that they do have a very large energy gap. And therefore, at least if we are in the infrared or in the visible spectrum, there will not be interband transitions in insulators either. So we really need to go to very high frequencies, so around the ultraviolet region, to have transitions in insulators, right? At a bit, let's say, low energies, you can have some very small absorption peaks due to the creation of excitons. You might be wondering what an exciton is. That's another quantum concept. An exciton is basically when you have a pair of an electron and an electron hole, and they both are attracted to each other by a force that is called an exciton, right? And due to that interaction, you can have some very small absorption peaks below the gap energy in insulators, right? But other than that, you won't really see well-defined nice peaks, right? Like you see when you are, let's say in this case, in the ultraviolet region for semiconductors, if you are in the visible region, right? Or same for metals. Okay. That's why insulators are transparent from the far infrared region all the way up to the UV region, and then in the UV region is when they become opaque, right? When you start seeing absorption. Okay. As I said, there might be a case where when you have excitation of phonons by photons in the infrared region for insulators. It's, how to say, it's just complicated. I don't want to get into that. Just may take into account or keep in your mind that there might be some absorption mechanism in the far infrared region, or let's say small frequencies. But again, you won't really see a nice, well-defined peak. Okay. Let's see the comparison between different type of glasses, right? So if you look at fused quartz, you will see completely transparent material between 0.29 electron volts and 6.9 electron volts. With two peaks around 1.38 and 2.8 micrometers, a very minor peak around 1.24. That's for fused quartz, so for a crystalline material. Now, if you look at window glass, which is basically the same material with some impurities, you will have a similar transmission spectrum, but obviously you will cut, you will have a UV cutoff wavelength around 3.3 electron volts, so up to there, and then because it's a material that is not crystalline, you just have a cutoff there. Now, if you compare that traditional window glass to a sol gel silica glass, so a bit more crystalline glass, you will see that there is no peaks, or the peaks that you had around 1.38 and 2.8 micrometers, they disappeared, and that's why that is the only material, the only glass that can be completely transparent from 0.16, sorry, that should be micrometers, not millimeters, that should be micrometers, to 4 millimeters. Okay. Now, let's look at the glass for optical fibers, the borosilicate phosphosilicate glass. You can see you have peaks, but they're not sharp, they're not well defined. You can see at 1.3-ish and at 1.2-ish, so that small peak there, and then you have another peak at around 1.55. So you can see there are peaks, right, for these materials. And they actually happen by the vibrations between the hydroxyl ions, so the OH ions. So there will be in this glass there will be some traces of these hydroxyl ions, and once you are at those frequencies, there will be those stretching vibrations between these ions, and that's why you will see these absorption peaks, right? Otherwise, you wouldn't have any of them. Okay. Now, what happens with the opacity of some dielectric materials, right? Because, for example, opals, enamels, porcelains, they should all be transparent because they're insulators. Why are they not transparent in the visible region, right? If we're saying, oh, wait, so they are insulators, they should be in the visible region, they should be transparent, right? Wait, well, that is because, all of these materials have certain particles in the matrix. And those particles are the ones that are scatter light when light is coming in, and that generates opacity, right? So part of the light is transmitted, part of the light is reflected, because of those small particles, impurities that you have in those materials, right? That's why actually you, let's say if you actually want to make a dielectric material, make it opaque, you actually put particles there in purple so they can reflect some light. Okay. Okay, you have another applications. You have other applications, and actually, so far we've dealt with absorption of light, but you can also have emission of light, right? So far we've seen everything with absorption, but you can have emission, and actually emission of photons, right? Once you excite an electron, eventually the electron will have to revert back into a lower empty energy state. So it's not just, so far we've seen just that excitation, that you move to a higher energy state, but eventually it will have to come back to a lower energy state. So that, let's say that reversion, right, that is usually in a fraction of a second, will be accompanied by emission of a photon, right? Or that can also be that can also go along with a dissipation of heat, so phonons. So basically, when the electron is coming back to a lower energy state, you can emit photons, or you can also emit phonons, or that is dissipate heat, right? And so depending on how quick that reversion happens, you can have a phenomenon called luminescence. That's what you call luminescence. If that transition back to a lower energy state happens in nanoseconds, that is the fluorescence. If it takes microseconds or milliseconds, you have phosphorescence. Or if you have actually, it takes more time. Actually, it takes seconds to do it. Because electrons are trapped in some impurities and things like that. Well, that is called afterglow. So, but all of these are basically luminescence phenomena. It just depends on how quick they happen. Okay. I can have other applications like photoluminescence. That is when photons impinge on the material and re-emit light of lower energy. Electroluminescence, and that is when the material emits light as a consequence, or when I apply a voltage or an electric field. And that is, for example, the best for LEDs, for light emitting diodes. Or the application of that is the LEDs, right? The screens, for example, or the light. You've heard a lot the LED light. Cathode luminescence, that's what we had before, the traditional lamps that you had before. Okay, so you can read that. That's just more like for your information what applications you have. Then you have the thermoluminescence and the fluorescence, between comparison between traditional light and the new fluorescent, more efficient light. And here is just how it works, right? So you have the tube that is usually filled with low pressure mercury, and you have both ends of the bulb connected to tungsten filaments. So when you lit the filament, electrons are ejected in an accelerated electric field. They between the two electrons, and that obviously generates a plasma, and that plasma emits ultraviolet light, and that ultraviolet photons are absorbed by a phosphor, and that emits light, right? And depending on the type of phosphors you have, each phosphor will have its characteristic color. That's why you will see some lights, some LED lights, some fluorescent lights that are very white, some of them are a bit more yellowish, some of them are a bit more bluish, and that will just depend on the type of phosphors that you have, right? Usually they will have 3 to 4 phosphors to give sort of a large range of different colors that LED lights can take. Okay, these phosphors are usually metal sulfides like zinc sulfide, or just organic substances, right? Like zinc oxide, for example. They are, that's what the phosphors are. And they obviously are at very high temperatures, right? 3000, 3500 Kelvin, 4000 Kelvin. And that will also affect the color of your light. And then you have lasers. You have, well, LEDs, as I already said. You have organic photovoltaic cells. You have LCDs, so liquid crystal displays. So everything what you have in your at home, I guess, your TVs, your video cameras. You can apply all optical properties in photonics. So photonics are just crystals that relate, such as the interaction, similar to the interaction of electrons. Here you're just dealing with the interactions of photons, right, and photonic crystals. So like, you know, crystals that are have a periodicity of the dielectric constant. So it's literally like similar to electronic behavior. Then you have the optical storage devices, so you know, the CDs, the DVDs, the Blu-rays, and everything. The optical computers. Optical computers are computers that work with infrared light or visible light instead of working with electrical current. So they use, or they use basically visible light or infrared light to perform calculations, right? Rather than electrical current like a traditional computer does. And you can also generate X-ray emissions, for example, and you know that is using medical applications, also in industrial applications like characterization of materials. Okay, so bunch of applications. And that will be it, guys, for this module. I'll see you on Wednesday. Any questions? The slides are already uploaded, so you can go and look at the slides. And that will be it for today, if there is no questions, guys. Yeah, I'll the coffee break, I'll talk to the people that had to do it today, and I'll figure it out. Okay, you might have to record the coffee break, or just connect 10 minutes on a time that is not, I guess, in class time, and I'll just we'll just do it like that. I'll figure it out. Okay, I'll contact you, and I'll let you know how are we gonna do with that. Okay, thank you, guys. Well, oh, okay, Nati. Yeah, it's Nati and Georgina. Okay, that'll be it for today's class. Take care, guys. Have a good day, and see you on Wednesday.
Thanks. Have a good one.